Alright, we will be talking about clustering today. That's yet another unsupervised technique. Principal component analysis and dimensionality reduction, the topics we covered last week. We started the unsupervised learning, and in this week we will be talking about clustering. That's yet another unsupervised learning technique. As usual, we will start with the summary of the last week, and then we will continue with two different clustering techniques, namely k-means clustering and mean-shift clustering. So what we covered last week, actually we covered k-nearest neighbor algorithm. That's a pretty simple algorithm in order to classify the unknown things, such as this one. We have seen that as the k increases, the decision boundary gets smoother, and we have seen the concept of principal component analysis and dimensionality reduction, and we have seen some applications of principal component analysis. Starting with k nearest neighbor algorithm, that's a pretty simple algorithm. Basically, you just check the neighborhood of the new coming sample, such as this one. This is the new coming sample. Let's assume that we would like to use k as 3. We would like to take a look at the first 3 neighbors of these newly coming elements. And by using the majority voting, which means whoever has the highest votes, we assign the class of these samples. Such in this case, the blue samples have the high voting, so we assign blue to this newly coming sample. We have seen by choosing different k's, the output may change. Okay, that's why we say the boundary becomes smoother with increasing k. So just be careful. By increasing the k, we increase, for example, in this case, the newly coming element, this one, will be classified as a triangle, right? If you choose k as 3. But if we choose k as 5, then the first 5 neighbors will be these 3 blue rectangles and then these 2 triangles. Therefore, if we choose k as 5, then we need to assign rectangle to our newly coming elements. But if we choose k as 3, then we should assign triangle to our newly coming elements. Okay, so that was basically the idea behind the k nearest neighbor algorithm. And we have seen 3 distance metrics: Euclidean distance, Manhattan distance, and Chebyshev distance. And basically they are called Minkowski distance family. Okay, and when we say Euclidean distance, it's basically the closest distance between 2 points. That's the flying distance. If you consider this as a city, these are the roads of the city, these are the blocks of the city. Okay, if you have a helicopter, if you can fly from point A to point B, that's the Euclidean distance. Okay, if you have a car or if you walk, then you need to use the roads, right? Because the blocks are blocking your way. This is called the Manhattan distance or the city block distance. Okay, and if you are using, as the king in chess game moves, such as you can either move diagonally or you can move in this direction or in this direction, then that's called the Chebyshev distance. Okay, and all 3 have different usages. Usually we use Euclidean distance with our calculations. Sometimes we use Manhattan distance. Sometimes we use Chebyshev distance. So they are called Minkowski distance family, and they share the same equation basically. By just using p as 1, we obtain Manhattan distance formula. If we use 2, we obtain Euclidean distance formula, and if we use p infinity, then we obtain the Chebyshev distance formula. And basically, if we are using Euclidean distance, then the distance to go in these directions are 1, and if you want to go diagonally, the distance is 1.4. Okay. If you are using city block distance or Manhattan distance, if you want to go diagonally, the distance is 2. Okay, because you need to go here and then here, or you need to go here and then here. But in Chebyshev distance, since this is moving like the queen or the king in chess game, all distances, all 8 neighborhood distances are 1. Okay, that's an important concept. And we have seen some stuff about KNN. We have seen that that's a lazy learner. That means it's not basically training a model. KNN makes its predictions just in time by just calculating the similarity between an input sample and each training distance. There are many distance measures to choose from, and we have seen in the example we did last week, Manhattan distance basically gave a better result than Euclidean distance. And if you're using KNN, it's a very good idea to rescale your data, otherwise you will have a lot of trouble. And we have seen a concept called curse of dimensionality, which means as the number of independent variables increases, the performance may decrease because the distance between 2 points may lose its meaning if you have too many independent variables. Okay, that's called curse of dimensionality. And we have seen the concept of dimensionality reduction. That's basically, we have seen principal component analysis with the dimensionality reduction. We have seen 3 steps. First, we do a standardization, then we compute the covariance metrics, and then we compute the eigenvalues and eigenvectors of the covariance metrics. Okay, be careful with these definitions. You may be encountering them in the examination. And the meaning of principal component analysis is basically the first principal component carries most of the information of your data, such as in this one. So this is the first principal component, this is the second principal component. And basically, most of the information lies within the first principal component. Okay. And we have seen an example on MNIST database. We basically reduce the dimension of our image, and then we rescaled our image. Then we could reconstruct our image with 95% information preserved, such as this one. Okay, and we did another example, and we use inverse transform, principal component inverse transform, in order to reconstruct or regain our reduced dimensions. Okay, please just remember this inverse transform. Remember this one, the most information is covered in the first principal component. Okay, and revisiting the quiz of last week, which distance metric is basically all metrics can be used by the KNN. KNN stands for K nearest neighbor. KNN automatically computes the number of classes. That's basically false. As the value of K increases in KNN, the decision boundary becomes smoother. PCA can be used to reduce number of independent variables. That's basically the idea behind PCA. As the number of features increases, KNN may suffer from curse of dimensionality. Yes, that's true. PCA is calculated from eigenvalues and eigenvectors of covariance metrics. Please remember this. PCA stands for principal component analysis. Decision tree can handle unbalanced data very well. That's false. PCA component that describes the data more is the one with highest eigenvalue. That's true. Alright, let's start with the content of this week. We will first start with the definition of clustering, what clustering means. But before doing that, let's remember this nice image. So we have machine learning at the middle. Okay. Up until now, what we covered was mostly supervised learning. Okay, we worked on regression, we worked on classification, we have seen different classification techniques, we have seen different regression techniques, and all these techniques were using labeled data, right? Therefore, they were called supervised learning. And with dimensionality reduction, with principal component analysis, we started the unsupervised learning. Okay, with the unsupervised learning, we don't need any labeled data, and the concept clustering that we will be seeing in this lecture, we don't need labeled data either. So that's an unsupervised learning technique as well. So clustering is an unsupervised learning method, and cluster analysis or clustering is the task of grouping a set of objects in such a way that objects in the same group are more similar to each other. Okay, and these groups are called clusters. In this image, objects that are close by distance are clustered into the same group. Okay. And central to all of the goals of cluster analysis is the notion of the degree of similarity or dissimilarity between the individual objects being clustered. A clustering method attempts to group the objects based on the definition of similarities applied to it. And we usually use the distance as the similarity. And in K-means clustering, the first clustering technique we will be seeing, we will be using distance as the similarity measure. So what do we mean basically by clustering? We have a data like this, okay? There is no label. And then we somehow cluster these samples in a way that closer samples stay in the same group. And these groups are called clusters. Okay, so this is cluster 1, this is cluster 2. And similar here, these 5 samples, for example, stay close to each other, and these 6 samples stays close to each other. Therefore, we create 3 clusters or 3 groups, and basically samples that are in the same group are classified as the same class. Okay, things to consider while doing clustering. First of all, there is no best clustering algorithm. We will be seeing 2 clustering algorithms, but there are quite a few algorithms in scikit-learn. I will show a sample, but there is nothing like the best clustering algorithm. That totally depends on your data, that totally depends on your problem. Okay. Some clustering algorithms require you to specify or guess the number of clusters, or they require you to guess some parameters. Okay. And some algorithms require the specification of some minimum distance between the observation in which samples may be considered closed or connected. So you may need to specify some parameters in clustering. Okay, these are basically some clustering results for some sample data from scikit-learn. That's an image from scikit-learn. Basically, you can see the names of the clustering techniques here, and you can see different data sets, okay, with different samples. But you can observe from these images, as I mentioned in the previous slide, there is nothing called the best clustering technique. Okay. Let's look at this example. For this example, from my point of view, this is kind of an okay clustering, okay, because it clustered the outer layer and the inner layer into 2 clusters. This is garbage, this is garbage, this is garbage. So this is okay. So spectral clustering did a good job for this example, as well as this clustering technique, and this one did a good job. Let's take a look at this sample data. What I would expect, this should be one cluster and this should be one cluster because they are connected, right? Although they are close to each other, these guys are connected, but these 2 classes are not connected. And as you see, the spectral clustering did a good job. These 3 guys created garbage. In this case, this created an okay result as well. For the first set, this was garbage as well. So basically, they are creating good results for this data set, these other clustering techniques. When you look at this data set, most of them are doing kind of okay, because that really depends on the distance between the samples. But when you take a look at this data set, again, this is producing garbage, this is garbage, this is garbage. In this case, spectral clustering kind of get confused with this data, but it's doing okay. This is kind of garbage, this is garbage, this is fine, and this is fine as well. So this is an easy example, right? And as you see, all the clustering techniques made a good job with this, because they're not close to each other. The classes are pretty distinct. So all the techniques in scikit-learn could be able to cluster them in a good way. And this is a pretty complicated example. And as you see, most of the clustering algorithms failed, basically. That's kind of fine. This is kind of fine. This is kind of okay. And this is kind of okay. So moral of the story, there is nothing called best clustering technique. The technique you should be choosing definitely depends on your data. And you need to try most of the algorithms in order to come up with a reasonable one. Okay, so let's work on the clustering techniques. We will be starting with k-means clustering. So that's a very simple clustering technique, basically. And this animation is showing how it really works. Initially, we need to select the number of classes. That's the thing about k-means clustering. You need to select k. For example, in this case, we select k as 3, which means we would like to have 3 clusters at the end. Okay, and that's the thing with k-means clustering. You need to select k. There are some methods that we will be covering in order to select k automatically, but you need to assign the algorithm a k value. And then we randomly initialize the center points. Okay, these are randomly initialized center points. The things that are moving in the animation, they are the center points. Okay, and each data point is classified by computing the distance between that point and each group center. So once we select the group centers, in this case we would like to have 3 clusters, so we initially created 3 centers, and then for every point you see in the samples, we create a distance between that point and the cluster centers, and then we assign the class of the closest center. In this case, for example, these guys are red by now because they're closer to red, and these were blue because they were closer to blue. But once this moved to here, these guys became red. Okay, and then basically iteratively we compute the cluster centers, and either at the end of the iterations, or if the centers doesn't move a lot, then we commands there. Okay, so we stop the algorithm. Let's see it on a simpler example. For example, we would like to cluster these guys, and when you look into the samples, you would expect 3 clusters, like, so this should be one cluster, this should be one cluster, and this should be one cluster, because these are closer to each other, right? So the clustering, the ideal clustering should give something like this. Okay, so let's start the k-means algorithm. So we randomly select, in this case we would like to have 3 clusters, right? Because we see we need 3 clusters, so we selected k as 3, and then we randomly select k data points. So we selected this, and this as the initial cluster centers. Okay, this was the initial step. We selected k, and we selected k number of initial cluster centers. Then for each point, we need to calculate the distance between that point and the cluster center. Okay, in this case, this is a 2-dimensional or one-dimensional example. So this is the distance between this sample and the cluster center of blue class. This is the distance between this sample and the green class center, and this basically is the distance between this sample and the orange cluster center. Okay, and we assign blue to this sample because it is closest to the blue sample, blue cluster center, right? So now we are done with basically this sample, and we repeat the same for the second element. So we calculate the distance between this sample and blue, this sample and green, and this sample and orange, and then we assign green because it is closest to green, right? And then for this sample, we basically calculate the distance between the sample and the blue center, this sample and the green center, and this sample and the orange center, and then we assign orange because it is closest to orange. And once we are done with all the samples in our data set, we come up something like this. Okay, this was the first iteration basically, and then we recalculate the cluster centers. Okay, initially the cluster centers were these big bubbles. Now we need to, for the second iteration, we need to recalculate the cluster centers, and basically the cluster centers will be these guys. Okay, and then we repeat the same procedure. But once we repeat the same procedure, we calculate the distance between this guy and this guy. The cluster centers will not change. Okay, so our initial random cluster centers cluster these data sets in a way that we have this cluster, we have this cluster, and we have this cluster. So this is what we got, and this is what we were expecting. So this is basically garbage. This is not something good, right? But this is how K-means clustering works. So can we do something for that? We got this clustering because we created our initial centers randomly. If, for example, our initial centers were here, here, and here, we would come up something like this. Okay, but since we used random cluster centers, the first clustering output is this one. So we have a method to compensate for this. Okay, once we are done with clustering for this first randomly selected cluster centers, we calculate something called total variation. Okay, that's basically the variation within each class. So for this class, for example, the variation is small because they are close to each other. Okay, the variation is basically the distance between the cluster center and all the samples. So the variation here and here is pretty small, but the variation in this class is quite high because the cluster center is here, the cluster center is here, and the variation, the distance between all the samples to the cluster center increases as we go to the left or to the right. So we have something like this, total variation. And once you look at this visually, you see that this is unbalanced. Okay, and in order to select a good clustering result, we would like to have this total variation balanced. So what we do basically is we choose more random initial cluster centers and we repeat the whole clustering procedure, and then we come up with more total variations, and then we compare all the total variations. Such, let's say we did 3 attempts, and out of these 3 attempts, so this is not good, this is unbalanced as well, this is very unbalanced as well, but as you see, the second attempt is quite balanced, so we would choose this as the winner clustering, and that would classify our data sets in a better way. Okay, Concerning the selection of k, there is a technique called elbow technique. That's basically checking the total variation as well. And once you choose different k values, you come up with different total variations. And as we increase k, total variation decreases. But there is one point per cluster, total variation becomes zero. But we don't want that. That's not something good. Because if you select k1, k as 1, then the total variation will be pretty small. So with the elbow technique, basically you look and edge something like this, okay? And for example, for this example, when k is equal to 3, you have this edge. You have this breakdown, okay? So it's a logical idea to choose k as 3 by just using this elbow methods, okay? What if we have two-dimensional data? The example we worked on is one-dimensional. What if we have two-dimensional data? We then basically use the Euclidean distance in 2D. Instead of calculating the distance between these points in just 1D, we calculate the distance in 2D. Okay, that's basically the same thing. Okay, we will be doing a small example concerning the k-means clustering. But in order to visualize the cluster boundaries, we need to install ML extents. So just please follow the instructions here with your Anaconda virtual environment and install ML extent. Then you will be fine with the incoming example. So let's see. As we usually do, we first import the required libraries, and then we import from the datasets what's called the make blobs, and then we will be doing some blobs, and then we will be plotting them. Okay, once we plot them, you see there are 5 natural clusters. But when you take a closer look at the clusters, for example, you can split this cluster into 2, or you can split this cluster into 2. They don't need to be just one clusters, okay? So in order to use k-means from scikit-learn, we basically import k-means from sklearn cluster. And as we usually do, we first make a definition. Once we're doing the k-means definition, we need to assign the number of clusters, okay? And in this case, let's try to cluster this data into 9. Naturally, we should be clustering this data into 5, right? Because what we see is this is 5 clusters, basically. But let's try to cluster this into 9, okay? This is the definition. With this, we are just training the model. That's pretty fast, actually. And then let's make the predictions for our all x values, and then let's try to plot them. You see, we wanted to have 9 clusters, okay? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. You see different colors for different clusters. You see the cluster centers in red. Since we wanted to have 9 clusters, we have 9 clusters, okay? If we wanted to have 5 clusters, that we would gonna have basically have 5 clusters. Let's try to make that. You see, that's more reasonable. What if we wanted to have 3 clusters? Whatever, you have 3 clusters. This is the cluster center for this cluster. Since these are closer to each other, we are basically clustering this into the same class. And since they are closer to each other, this is one cluster and this is one cluster. So you can basically define any number of clusters. That's not gonna exceed the number of samples in your dataset, but Basically, by using the elbow method, it's a better idea to uh, make a prediction for a better k. Now let's go back to our k is equal to 9. So we have now 9 clusters. And in order to see how we basically split the space, we will be using the ML extents plotting facilities. And you see, these are basically the class boundaries or cluster boundaries. It's always a good idea to see this because whatever falls into this region, okay, will be classified from this class, and whatever falls in this region will be classified as this one, and whatever falls in this region, for example, will be classified in this one. Okay, it's a good idea to take a look at this ML extent plotting facilities. It's giving you a much better idea how we basically split the space into clusters. Okay. Now let's go back to our k-means. So what are the advantages? It's pretty easy to implement. It's pretty fast. Disadvantages that requires number of clusters to be known, and that's not trivial. With the elbow method, you may not be able to find the best k all the time. As it starts with random cluster centers, it may yield different clustering results, and sometimes these clustering results may not be ideal, as we have seen in our example. We have started with random class centers, then what we came up with was not basically the ideal cluster we were looking for. Then we did repeat the procedure a couple of times, and then we came up with much better total variation. So the second clustering technique we will be working on today is called mean shift clustering. And mean shift clustering is a sliding window based algorithm that attempts to find the dense area of data points. Okay. And as you see in this animation, we basically start with the random points and we create a neighborhood within a circle, and then in this circle we calculate a center of mass, okay, and then we move towards that center of mass. And since we are moving towards the center of mass, we are basically moving to a denser area in each iteration. And once we are not able to move, once we're in the denser area, then the algorithm stops. And we start with another point, and if that point is not classified, then we classify this point by following the sliding window. So basically these are the steps of the mean shift algorithm. Let me show you on the animation. We start, this is the initial point, okay, and this is the region we are calculating the center of mass from, and all the samples falls within this region. We basically calculate the center of mass, and then we move towards that center of mass. That's why it's called mean shift clustering. You first create a mean, and then you shift that mean in the direction of a denser area. Okay. Let's try to make an example. So this is our sample data. Okay. And this is the point we're interested in. And this is the radius, this is the circle that we will be using in order to create our new mean. Okay. And basically we take the samples that falls within this circle. So these are the samples that falls within this circle, and we recalculate another center of mass. Okay. This is, for example, this is the new center of mass for the circle. Okay. And since the algorithm is called mean shift clustering, this was our initial mean, and this is how we will move. Okay, so we will move towards this direction. So this center will move to here. Okay, in the second iteration. Now that we move here, the circle, the diameter of the circle doesn't change. Okay, but we have new samples inside our circle. So we need to calculate another center of mass from these samples. So this is the new center of mass for the samples. Okay, and then we move our center from this point to the new center of mass, as in this one. Okay, and then we repeat this procedure until we come to the densest area. Okay, in this case, this is the densest area, right? And once our moving window or moving circle comes to this point, then we don't move anymore. And all the points we pass through, we assign the same class. Okay, and this point is called a point of attraction, okay, or an attraction center. And let's say we are working on more complicated examples such as this one. As you see, we have two attraction points, right? Wherever you start, for example, if you start from here, then somehow you will be coming to this attraction point for this side. And if you start somewhere here, for example, you will be following a path something like this, because this is going to a denser area, and then you will end up in this attraction point. Okay, so these attraction points are called cluster centers for mean shift clustering, and the points you passed, you assign the same class, okay, such as this one. So we have these two attraction points. For example, we start from here, we follow this path. For all the points on this path, we assign the same class. Okay, and we start with another random point. We follow this route because it's going to a denser area. Then we assign all the samples to the same class. So we have two attraction centers for this example. Therefore, whatever point starts from this region that ends up here, and whatever sample from this region ends up here with the mean shift algorithm. That's why it's called mean shift, because we are basically moving its mean. Okay, let's say we started from this point, we have a mean somewhere here, and then we move towards here. We are going to a denser area by moving towards this direction. We move to denser area, denser and more dense, and then we come to the densest point or the attraction point of this cluster. So mean shift clustering doesn't require you to give the number of clusters. It's basically doing that automatically. The only parameter you need to assign to mean shift clustering is this circle radius. Remember, so this is our circle that we use to calculate the center of mass within its territory. Okay, you just need to assign the radius of the circle, and depending on the radius of that circle, you may end up with different results with mean shift. So let's take a look at the example from scikit-learn. In order to use mean shift from scikit-learn, we need to import mean shift from sklearn cluster. So that's an iterative algorithm. Therefore, we import these guys as well. We create our models, and then we learn from our models, and then we basically get the cluster centers. Remember, the cluster centers are the attraction points in mean shift, and then we assign some labels. Let's just plot our cluster centers. Okay, In this case, mean shift automatically clustered our data, the previously used data, into 5. So we have 5 cluster centers, we have 5 clusters. We didn't say create 5 clusters to mean shift, right? That's what we did with k-means. We specifically said k-means to create 5 clusters or 9 clusters or 3 clusters. With mean shift, we just assigned the circle radius, okay? And it could be able to basically create 5 clusters. Okay, let's go back to our slides. So, advantage of mean shift clustering: there is no need to select the number of clusters, as mean shift automatically discovers this. The disadvantages: it's very slow. It's really slow. And the selection of the window size or the radius of the R is non-trivial. If you select it too large, then your clustering results change. If you select it too small, it behaves more differently. So there is no trivial way to select the R, and it's really slow. Let's remember this image from scikit-learn. What we have seen is basically there is no ideal clustering technique. Even if you look at this, the clustering, spectral clustering seems to be doing well with most of the data. It's not doing well with this data, for example. So there is no ideal clustering technique. Don't forget. The mostly used clustering techniques are k-means clustering and mean shift clustering that you will be hearing a lot. But there are a lot of other techniques, more complicated techniques. But anyway, there is no ideal clustering technique. So let's sum up this lecture's content. We have seen k-means clustering. We basically select the number of classes, randomly initialize the cluster centers, and then calculates the closest cluster center. And with respect to the closest cluster center, we assign cluster values to all the samples. And we repeat this procedure until we come to a stable clustering with the k-means, okay? And with the mean shift clustering, we basically start with a random point, and then we follow the direction that's going to a denser area. And we don't need to assign any cluster number with the mean shift algorithm. We just need to select the search radius for the algorithm.